So actually what happened is that there was an initial phase from the 80s to more or less 1992, during which the scaling was done at a constant voltage. Essentially this means that the supply voltage was kept at 5 volts. And this was basically required to maintain back compatibility with all the previous TTL logic families, the BJT based logic that had a supply voltage of 5 volts. So by keeping a constant supply voltage, the good part was that one could simply substitute chip for chip in a same board and be sure that the integrated circuit would behave properly. Okay, because of course the supply voltage was exactly the same. In terms of the generalized scaling that we have discussed now, it means that this lambda factor was equal to 1 and that only the geometry was varied, so S was larger than 1. What is the main problem? Let's say lambda equal to 1 and S of course is larger than 1. We can have a reduction of geometry, but at some cost, because as you see here, if you have constant voltage scaling, the power consumption increases because you have the power consumption is constant because lambda is equal to 1. So the power consumption of a logic gate, when you decrease the logic gate and you increase the clock frequency, remains constant, but the area goes down as 1 over S squared. So the power consumption per unit area goes up as S squared. Okay, so what are the implications? PD over area is proportional to S squared. You have an increase of power density and at some point it is not sustainable anymore, because of course, since the total area of the chip is not decreasing, but you're putting more logic gates on the single chip, you have a strong increase in the total power consumption. If you assume that the total area of the chip remains constant, it is actually not true, because also the area of the chip is increasing. But let us assume for the moment that the chip area becomes constant. The power consumption of the whole chip goes up as S squared. So generation after generation, you have an increase of the total power consumption that at some point becomes unsustainable. Okay, and this was the reason why from 1992 the supply voltage started decreasing. Okay, of course you lose something when you decrease the supply voltage, because you can you can increase the clock frequency at a much slower pace, and in addition to that you lose back compatibility of the new integrated circuits with the circuits that you had before. Okay, but it's the only way to continue, because otherwise the total power consumption is not sustainable. Therefore, we have phase 2, which is basically from 92 to 2002, something like that, 10 years, during which we had constant field scaling. Constant field scaling means that we scale with the same pace both the voltages and the geometry. So the electric field, which is the ratio of a voltage over a length, becomes constant, and therefore in our terms it means that we keep lambda equal to s. So we scale with the same ratio both lambda and s. Okay. There are two advantages in doing that. One advantage is that you do not increase the electric field too much in the device, because at a constant voltage scaling you keep the voltage constant and you decrease the dimensions. It means that you are increasing the electric field in the device, and this is no good for reliability, because the reliability issues are related to the intensity of the electric field in the device. Then the other advantage, which is the one that I mentioned at the beginning, is that you at some point you do not increase anymore the power density per unit area. If you remember what we wrote here, if lambda is equal to s, the power and the area scale as 1 over s squared. They both scale with the same pace, and therefore their ratio is constant. So constant field scaling means that PD over A is constant. So this is a constant power density per unit area. So the great advantage is that if you keep the area of the integrated circuit constant, the total power consumption of the integrated circuit is constant. Let's assume it is a microprocessor. The total power consumption of the microprocessor is constant, but of course you have a significant improvement in performance, because when the number of logic gates scale as s squared, because the area goes at 1 over s squared, and the clock frequency is increasing. It is at the same time scaling as s. So let's make a note. Performance, computational performance, computational performance is proportional to the inverse of the area, because at a constant area of the chip, the number of logic gates that you can put on a single chip is proportional to the inverse of the area of a single logic gate times the clock frequency. So it goes up as s to the third power. So there's a huge improvement in computational performance at constant total power. And this has been one of the main engines of growth for the whole electronics industry and for the whole information technology. At a constant power, you could, if you could double, if you could cut in half the linear size of a transistor, you could multiply by 8 the performance of the chip at the same power consumption. Okay? And in this time, for example, from 92 to 2002, for example, the gate length went from 0.5 micron to 0.13 micron, so it's a huge reduction. The supply voltage went from 5 volt to 1.5 volt, so you see it's almost the same type of scaling. Okay, this is the type of improvement that we had in that time. But of course, this time ended because there was a problem at the end, and there were actually two related problems, again related to power consumption. And what happened is that the static power consumption, which was negligible up to this date, became really relevant. What are the main issues? One is this one. When you scale geometry in this way, you also have to scale the oxide thickness. And the oxide thickness, for example, from 2002, goes from something like 7 nanometers to 2 nanometers. So 2 nanometers is really thin as a gate dielectric, and actually at 2 nanometers the current going through the oxide is not negligible anymore. So we have the problem of gate leakage. Gate leakage is something that you can neglect completely when you have an oxide of 7 nanometers, because it goes exponentially with the thickness. But of course, it becomes critical when you have an oxide with 2 nanometers. And if you think in perspective, it becomes a really critical issue. This is the problem of gate leakage. But there is also another problem that is related to the threshold voltage, because the threshold voltage of the NMOS, of course, has to scale as the supply voltage, and for example, in this case, had to scale down from 1.5 volt down to something like 0.304. Let's write 0.4. Yeah, 0.4 volts. What is the problem? When you decrease the threshold voltage this much, you increase exponentially the leakage current, the I off that we have considered before. Okay, so essentially in 2002 there were two huge problems. On the one hand, one had to reduce the gate leakage. On the other hand, it was clear that one could not reduce the threshold voltage so fast, because the leakage current would be unsustainable, and therefore the static power consumption would increase too much. And for this reason, essentially what happened is that the problem of the gate leakage was resolved technologically by changing the material of the gate dielectric. I already mentioned this fact. By changing the material, by using these so-called high-K dielectrics, these new materials that could have that had a higher dielectric constant, so that you could have a thicker oxide, and then you could decrease the gate leakage current. The additional issue, the problem of the threshold voltage, was simply resolved by stopping the decrease of the voltages. So essentially we had to stop the decrease of the threshold voltage, and therefore also to almost stop the decrease of the supply voltage. So at some point, not exactly at 1.5, but at about 1 volt, the supply voltage stopped going down. Okay, but of course we go back to the problem that we had before. This increase of power density per unit area, and in order to solve this aspect, the only thing that could be doable was to reduce the clock frequency. Okay, so the phase 3 is the phase in which we are now. Phase 3 almost stopped, not exactly stopped because we have a decrease, but it's really slow. Stop the scaling, almost stopped voltage scaling. So this lambda is let's say 1. It's not exactly 1, it's something like 1.1. okay, but it's almost there, and therefore geometry scaling S, and then no increase or reduction of f clock. What exactly means that we do not increase f clock? It means specifically that we do not exploit the performance capability of the logic gates, because if you go back to this situation, of course you see that if we stop decreasing the voltages, this factor remains constant, but if we decrease the geometry, we continue the scale down of the geometry, the propagation delays are still decreasing. Okay, if we do not increase the clock frequency, so we do not go with S, but we stop, let's say, to increase the clock frequency, or we decrease it, we actually significantly do not use all the performance we have. And the only reason we do that is just because in this way we do not increase the power consumption as much as we would do otherwise. Okay, so for example, let's put some numbers to make the thing clear. PDD is CPD of a logic gate is CVD squared times f clock. So C is proportional to 1 over S. VDD is constant. F clock is, we keep it constant. Okay, and then we have that PD goes up to 1 over S. The area is proportional to 1 over S squared. The PD over area goes up like S. So the power density per unit area in this case is still increasing. So what we do in practice, this is the reason why what we do actually is we keep lambda a little bit larger than 1, and we reduce a little bit the clock frequency in order to keep the ratio of the power consumption over the area more or less constant. Okay, so if lambda is slightly larger than 1 and f decreases, we have PD over A almost constant. Oh, okay, is that clear? Why we do that? Because we still have a great advantage, and we have the big advantage in having the capability of putting more logic gates in a single chip, because the area of a single logic gate is still going down as 1 over s squared, so the number of logic gates is still going up as s squared at a constant total area, and we can increase the computational capability only by increasing the number of logic gates, even if we decrease slightly the frequency of operation. In order to do that practically, we need to use, for example, in a processor, multi-cores. And this is the reason why from 2002 the frequency of operation of the processors stopped, but the number of cores increased, and the number of other, let's say the amount of memory on chip, the cache on chip increased a lot, and so on. And this is also the reason why, if you look at the typical situation, an Intel motherboard of the 90s, the end of the 90s, had a chipset with several different integrated circuits for the different parts of the required for the motherboard, and now let's say year after year, all those capabilities are all integrated in the microprocessors, because we have room, we have lots of transistors that we need to put to use, so we have space to increase the number of processors and increase the memory and increase the other functions, put some GPU on the chip, and so on. Okay, let me just